Hello, this is Qianqian Shin. I will introduce our work on solving instance detection from an open-world perspective. Instance detection aims to localize object instances of interest in novel scene images, and these objects are specified by some visual references. There are two settings of instance detection. One is conventional instance detection. In this setting, all object instances are predefined during training. That means we can use their visual references as training data to train detectors. But the scene images are still unknown. Another one is novel instance detection. This setting requires object instances to be detected are defined only in testing time, and don't allow the models to be fine-tuned further during testing. The difference between two settings is whether object instances are predefined during training or defined on the fly in testing. Both settings of instance detection are facing the open-world challenges. We have no knowledge about the testing data distribution, the arbitrary occlusions, the background clutters. In particular, objects can be novel and are only defined during testing in the novel instance detection setting. Meanwhile, InSDET models must be capable of detecting any object instances of interest and robustly comparing them with visual references. Existing methods exploit the open-world information in different degrees. An early method cut-paste-learn collects random background images from the open world to model diverse testing scenes, cuts instances from the visual references and pastes them on these background images to construct a synthetic training data. This approach partially addressed the unknown testing scene distribution. To mitigate the domain gap between detected proposals and visual references, a recent work attempts to learn feature representation from instance-level matching by using external datasets. This data utilization can be considered as data collection in the open world. Another work uses off-the-shelf pre-trained foundation models to improve proposal detectors and feature representations, which is applicable in both CID and NID. Existing methods address open-world issues by sampling data from the open world and adopting foundation models pre-trained in the open world. These motivate us to develop an InSDET method in the open world. We find that open-world detectors can detect objects with a very high recall, but foundation models are not tailored to instance-level matching between proposals and visual references. Let's focus on instance matching and fine-tune the pre-trained foundation model a little bit. In the open world, we are not short of data. How to leverage the data, the real data and synthetic data, is also a question. We have a natural, of course, open-source images in the open world. We can download or capture some photos, then run any open-world detector and segmenter like SAM to get foreground object instance. These foreground object instances are not what we care about, but we can use them as a distractor. These are negative examples to use Learn Better model. This is the first practice we sample distractors from the open world. The second is in the conventional instance detection, to bootstrap our training. We can capture multiple views of object instances. We have a QR code to estimate the relative camera pose and use NeRF to synthesize novel views to augment more positive examples, so that we can do metric learning to fine-tune foundation model. The third is to fine-tune DI-No V2 with metric learning loss. For example, we have an anchor, which is the first image of the dog, and we have another view, which is in the middle. And we have sampled distractors by running SAM, the negative example. We can use the triplet to fine-tune DI-No V2. The whole pipeline we can run object detector or open world detector, like SAM or grounding DI-No, or those famous ones to get proposals. Once we have the proposals, we run the fine-tuned DI-No V2 to represent the proposals as well as the visual examples, and we can construct a similarity matrix. Over the similarity matrix, we do a feature matching. This is the whole pipeline that we call solving instance detection from an open-world perspective, IDAO for short. We present the precision recall curves for representative instance detectors in both CID and NID, and we find our idols significantly perform better. The stronger open-world detector and feature representation improve InSDET performance. Here are some visual examples on a high-resolution InSDET dataset in the CID setting, and a Robotools dataset in the NID setting. Our idle outperforms other methods in both CID and NID settings. Thank you. Welcome to meet and chat with us in poster session. Please scan for our website for more information.